Log on, tune in, find out. Another good idea from Cambridge.
Douglas Bridges, coming to us from Christchurch, New Zealand. Hear about constructive thoughts on operator algebras.
Okay, if you're expecting something deep on von Neumann algebras, pretty much forget it, because as you'll see as the talk goes on, even the fundamentals of the subject are fairly resistant to any kind of constructive treatment. But let me begin, for those of you who haven't heard me talking before, and I see there's quite a few in the audience. What do I mean by constructive mathematics here? Let me say that there seems to me to be at least three ways, and perhaps three major ways these days, of approaching the notion of computability in pure mathematics. The first one is to use classical computability theory. There you're using classical logic and recursive functions or something equivalent to that, or possibly the Weierauch type 2 effectivity theory. The problem there, of course, is that the logic allows so-called decisions that can't be made by a real computer, at least with finite precision. And so in that case, you need a clearly specified type of algorithm, for example, a recursive function. So that's one approach, and it is, as the others are, perfectly viable. A second approach is relatively recent, the last 20 odd years, I suppose, which is proof mining, again with classical logic, and Ulrich Kohlenbach in Darmstadt is the prime protagonist of this approach. The problem I see with proof mining is that it does require an extremely heavy logical analysis in order to do what it aims to do, and it does that very well, to extract estimates, constructive estimates from classical proofs, this business of unwinding a classical proof to get the constructive content. It is, however, to me, not clear that this technique would work well within functional analysis or measure theory, let alone for the very non-constructive kinds of results that you have in classical operator theory. A typical operator algebra proof can be summarized by assume the object doesn't exist, do something or other, have at least one major application of Zorn's lemma, several pages of computation or several pages of mathematical manipulation, and then at the end you get a contradiction, conclusion the object exists after all. It's about as non-constructive as you can get, the typical classical operator algebra proof. And I really think you would be very hard pushed to extract from that any serious estimates that could be used in the data mining approach. The third approach, which is the one I'm going to adopt, uses intuitionistic logic. The idea is to shift your logic altogether into Brauerian intuitionistic logic with the so-called Brouwer-Heiting-Kolmogorov interpretation, and this logic is designed to capture the simple thesis that if you want to prove something exists, you have to show how to compute, construct, find it, at least to an arbitrary, specified in advance degree of approximation. And in this particular approach, the logic automatically takes care with the problem of those non-computational decisions which classical logic permits and which you have to overcome by imposing an algorithmic procedure into your classical logic. The other thing is that it enables you to work with any mathematical object. You don't have to work with some so-called computable object. You can just work with any mathematical objects, and you work in the familiar style of the algebraist, topologist, geometer, or whatever. So if you open up, for example, Bishop's book from 1967, if you open that up at a random page, you look at that, and your instinct is immediately, this is analysis. It's obviously analysis. Whereas if you open up at least some of the other books in the other areas I've talked about, you might be hard pushed to see this as analysis. You would certainly see it as, in some cases, very deep, technically deep logic with analytic consequences, but you wouldn't, as an analyst, think of that as being primarily analysis. So I'm going to talk within the framework of Bishop-style constructive mathematics, which affectionately we know as BISH, and for our purposes it is just mathematics with intuitionistic logic together with, well, you need some kind of foundation for your mathematics. So there's constructive set theory, a la Myhill, Peter Axel sitting here, and Michael Ratjen, or Martin Löf type theory from the Swedish school, as it were. And one more thing, dependent choice. We will freely use, and do freely use, dependent choice. But not, of course, full choice, because full choice implies the law of excluded middle. If we use intuitionistic logic, we can do a number of things. First of all, we can clarify distinctions of meaning obscured by classical logic. For example, there's a recent book that we've written which deals with an approach to topology through apartness. And this is a constructive approach. And there you find several different types, several different notions of continuity for functions between so-called apartness spaces. And in the classical counterpart theory, these all coalesce, they're indistinguishable. But constructively, they are quite distinct and have very special properties of their own. The second thing that you can get from this approach is that your results have a wide interpretation, a wide range of interpretations. For example, every theorem proved a la Bishop is first of all classically true. You do not prove within Bishop things that are classically false. Secondly, you have the recursive interpretation. You can impose the framework of recursive function theory on Bishop-style mathematics, and immediately, or not immediately, with effort, you can translate your results and your proofs into recursive theoretical ones. And also, you can translate it into intuitionistic mathematics if you want to. And there's this nice little quote from Bell and Machover that summarizes that point, I think, that intuitionistic logic is richer than classical logic, not more restrictive as people often think, because the former makes distinctions that the latter fails to make. Okay, now this is supposed to be about operators and operator algebra, so let me begin with operators singly and just highlight one or two of the things that distinguish the behavior of operators constructively in Bishop style from their behavior classically. So let's take a non-trivial Hilbert space. That means there's a vector with norm 1 in it. And B of H, the usual set of all bounded linear operators on H. Now, first of all, an element T, an operator on H, is said to be normed if its usual operator norm, its normal standard definition, exists. Now, constructively, it's not the case that you always have the norm for an operator. It's not always normed. Of course, in recursive terms, that means there is no uniform algorithm that will take an operator and will compute a norm for it. And the second definition we introduce here is, we say the element, the operator is jointed if it has an adjoint, defined in the usual way. And again, you can show that, if you think recursively, that the existence of adjoints for arbitrary bounded linear operators in Hilbert space would imply decidability for the halting problem. So normed and jointed, these are two things which don't always hold constructively, although they trivially do classically. Well, not quite trivially for having the adjoint. So here's the statement summarizing what I said. The two propositions, every element of B of H is normed, every element of B of H is jointed. They're essentially non-constructive. In fact, if they were true in a recursive sense, then you would basically be able to solve the halting problem. Now, here's a little bit of stuff about operator theory too. When does the adjoint actually exist? Is there a good criterion for the existence of the adjoint? The answer to this was given in separate bits by Ishihara and Richman in, I think, the 90s. So if I let ordinary B be the unit ball of H, then the criterion is this. If I have an operator T, if it's jointed, then the image of the unit ball is located. That is to say, you can compute the distance from any point X in the Hilbert space to the image of the unit ball. It's computable, it exists. So if you're jointed, then you map the unit ball to a located set.
Excuse me?
Yep.
Maybe I'll switch it off.
I'm sure that moment was captured on film. On the other hand, the operator is bounded and the unit ball is located, the image of the unit ball is located, then the adjoint exists. So for a bounded operator, the existence of the adjoint is equivalent to the operator taking the unit ball to a located set. And that's actually quite a useful criterion. And a similar sort of problem which has some significance for operator algebras, namely for trying to find range projections and so on. So here's a little question. When is the range of a jointed operator located? And is the locatedness of the range linked to the locatedness of the kernel in the way that it is classically, or to the range of T star, or whatever? Well, we need this little concept here. We say that the operator is weak sequentially open if for any sequence which T maps to, whose T values tend to 0, there exists a corresponding sequence in the kernel of T such that the nth term of x added to the nth term of y weakly converges to 0, in the usual sense of weak convergence for a Hilbert space. And this is indeed a kind of weak version of sequential openness, and that's why it's called that. And it turns out, this is a theorem of Ishihara and myself, the following are equivalent conditions for an operator with an adjoint. The range is located, the range of the adjoint is located, the kernel is located, and the operator is weak sequentially open, and the kernel of the adjoint is located, and the adjoint is weak sequentially open. So the simple classical result about the range of T and the kernel of T star and so on, that pulls apart, if you like, into this rather more complicated connection between ranges and kernels. And a question I want to raise, there's no way I'm going to get round to that one this week, but it's related to this. Is there a good criterion for the locatedness of the image of the unit ball under a linear mapping between simply Banach spaces, not just from a Hilbert space to itself? Now this is almost obviously going to be much more difficult. Banach space theory is a very deep and tricky subject, but it's a relevant question to the pursuit of constructive analysis. Is there a good criterion for an operator between Banach spaces taking the unit ball to a located subset? Okay, but let's get on to what I really want to talk about, I guess, operators in bunches. That is going to be operator algebras. Now there are three important, actually there's more than three, but there are three particularly important topologies on the space of bounded operators, on the Hilbert space. The first one is the uniform topology, which of course we all know about. Two operators are close if their difference has a small positive bound. And classically this is just the so-called norm topology, but remember I've already mentioned that the norm of an operator we may not be able to find it. So we can't discuss the uniform topology in terms of norms, but it's easy enough to do it in terms of bounds. The second topology is the strong operator topology, and that's the weakest topology on B of H with respect to which for each x the mapping which takes the operator T to Tx is continuous. And as you might have guessed if you don't know, there's a thing called the weak operator topology, and that's the weakest topology with respect to which for any pair x and y of elements of the space, the mapping which takes T to the inner product of Tx and y is continuous. These can all be described in terms of semi-norms and locally convex topology, etc. Now, a simple classical theorem is that the unit ball, B1 of H, the set of operators whose norm is less than or equal to 1. Now, if I write norm T less than or equal to 1 here, I actually simply mean 1 is a bound for T. It's a shorthand, not actually implying that the norm of T exists constructively. The unit ball is weak operator compact. It's a classical consequence of Tikhonov's theorem. It's a little tricky, but it's nothing terribly advanced. Constructively, the best we can do is to show that it's totally bounded in the locally convex topology, weak operator topology, and it's weak operator closed. But you cannot prove constructively that it's weak operator complete, which you would need to get compactness in the form total boundedness plus completeness. So it's closed weak operator in the weak operator topology, but if it were complete, then again it's a halting problem set up. Okay, now the provisional definition, if you like, of a star algebra of operators over H is a subalgebra of B of H with the property that for each element of that subalgebra that has an adjoint, the adjoint is also in the algebra. Of course, classically, every operator has an adjoint, and therefore the requirement is that the adjoint of T is in the algebra if T is. But for us, if the adjoint exists, then it's in the algebra. And the provisional definition of a von Neumann algebra would be a weak, I don't know why I've got the star in there, a weak operator closed subalgebra of B of H, which contains the identity operator, and whose unit ball, which is the intersection of the algebra with the unit ball of B of H, whose unit ball is totally bounded in the weak operator topology. Of course, classically, the last condition holds automatically because we know that B1 of H is compact. Constructively, we have to impose that. Now, a fundamental result at the foundation of classical operator algebra theory is one which characterizes weak operator continuous linear functionals on some linear subspace of B of H. And the characterization is that these functionals all have this form. They take the operator T to the sum of n terms of the type T xn comma yn in a product, where the boldface x, which is x1 up to xn, and the boldface y belong to h sub n. Now, h sub n is just the direct sum of n copies of h. So the classical theorem says that any weak operator continuous linear functional has this form for some n, some xn's andyn's, and also that these functionals coincide with the strong operator continuous functionals. Now, the classical proofs of these theorems depend on applications of non-constructive versions of things like the Hahn-Banach theorem, the Riesz representation theorem, the polar decomposition for operators, and so on. It's not to say that there are no constructive versions of those theorems, but the versions which are used in the classical characterization proof are non-constructive versions. And in fact, the constructive proof, and even the theorem itself is somewhat stronger to state, it's quite different. It's a totally different proof. It's a much more complicated proof, but you do get genuine algorithmic information out of it. And here's what it says. So let's take a non-trivial Hilbert space and a weak operator continuous linear functional on B of H. If it's weak operator continuous, then we have some data for describing that continuity. So let's put these data into the hypotheses. So let xi1 up to xi big N and zeta1 up to zeta big N be non-zero vectors in H, and delta a positive number such that this first displayed statement here holds. That displayed statement there is basically giving you the weak operator continuity of the functional U. Then the conclusion is that there exist points for little n going from 1 to big N, there exist points xn in the space of complex multiples of the nth vector xi n that appears at the beginning here, with the following property that U of t is the sum of txn and zeta n for all t in B of H. Now notice what you get from that. You get that the yn that was in the classical characterization, the yn in fact is given by one of the zeta n's that give the data for the weak operator continuity. And the xn is given as a multiple of a complex multiple of the xi n's, which give you the other part of the data for the weak operator continuity. So you get very explicit information in the proof about the nature of the xn's and the zeta n's that appear in the final result. And you can also prove, this by the way is recent work, it was done last year, that the classical proposition that if H is an infinite dimensional Hilbert space, then every strong operator continuous linear functional in B of H is weak operator continuous. You can prove that that's essentially non-constructive. In fact, it's again, I think, if I recall right, a halting problem business. So here is a classic example of where constructive intuitionistic logic teases things apart. Classically, strong operator and weak operator continuous functionals are the same thing. Constructively, they're not. you have this teasing apart of them. And what are the questions? Well, one problem is this: find reasonable conditions, and reasonable is obviously a matter of taste, reasonable conditions on a linear subset of B of H that enable us to replace B of H by the linear subset in the characterization theorem. You see, the characterization theorem was actually functionals on B of H. I would like to find good conditions on the linear subset where B of H can be replaced by something more general. Now, moving on a little bit, another fundamental result, a very fundamental beginning result in classical operator algebra theory, deals with the commutant and the double commutant of an algebra. So the commutant of a subset of B of H is simply the set of operators on H that commute with every operator in the subset. And the double commutant is what you'd expect, the commutant of the commutant. And the fundamental classical result is von Neumann's double commutant theorem, which says that a subalgebra of B of H, a subalgebra, notice, is, actually it's a star subalgebra of B of H, is a von Neumann algebra if and only if it equals its double commutant. And it's a beautiful result because, of course, being a von Neumann algebra is a topological kind of thing, and equaling your double commutant is a purely algebraic thing. So it's a wonderful link-up between the two. Now, the standard classical proof of that would actually go through, it would be constructivizable, to use the rather ugly word, if you could prove this little conjecture here, that if you have a von Neumann algebra, then for each x in a dense subset of the Hilbert space, the set algebra times x, which is the set of values under the values assigned to x under the operators A in the algebra, that should be located. So if that were provably located for all x in a dense subset, we could then push through the double commutant theorem. Of course, that's trivially located. Classically, locatedness is not a relevant notion in the classical context. In 2005, Bas Spitter has proved the conjecture and hence the double commutant theorem for commutative von Neumann algebras. But my interest is to prove constructively the general case of the conjecture without having a commutative subalgebra, and hence of the double commutant theorem. And in fact, I'm inclined to believe that you shouldn't need a von Neumann algebra. You should just need some kind of appropriate linear subset of B of H in order to get the locatedness that you're after there. And I have actually been looking at that this week. Okay, so finally, why would we want to investigate von Neumann algebras constructively? Well, the first reason, I guess, is because they are important in the foundations of quantum physics. They are extremely important in the technical foundations of that subject. Because the classical theory is beautiful and is a huge constructive challenge, as I've suggested, without any clear demonstration of that perhaps. It's a beautiful theory, it's an extensive theory, and it's extremely non-constructive as it's presented. And I guess a la mountains, because they're there as well. Okay, there's a couple of references, and I'm well inside my time. Good.
Thank you. Have you said how long you'll be here?
Oh, yeah, I'll be here till Friday and then Monday again, and that, I'm afraid, is all. Yeah.
Questions? I was going to ask, how is this work related to what Vasco Bratka and others are doing, computability of linear operators and so on?
Well, I might point out that every positive result we get can, I think, be translated into their stuff. Andre Bauer showed that some years ago. And of course, the negative, the non-computability results they get don't really appear in this framework because this is about computability. Everything, in a sense, is, that's what you get. You don't get non-computable things.
So we in computable analysis should be reading your papers closely.
Well, yes, I've been saying this for some years, actually, because in fact the computable analysis people have, in a sense, repeated a lot of stuff that we've done in 30 years. And added to it, I might add, but they have repeated it without realizing it was there.
Other questions? Oh, let's thank you.